So our next speaker is Michael Jordan. He is the chair of the Statistics Department at University of California, Berkeley. Since this is a very diverse audience for those of you who don't know him, he's one of the pillars of modern statistics, together with people like Rubin, Efron, Tipshirani, and a few others. His work is remarkable for breadth and depth, and he always gets at the fundamental ideas, and here I have a few examples. Early contribution in the theory of human cognition, statistical theory, modeling, and inference with applications to many fields, including biology and computer science. 10 years ago, he published a paper who essentially changed the way social and political sciences and beyond analyze text data. He is effectively credited with opening the field of machine learning. And recently, including, I guess, today's talk, he's going to talk about his new ongoing effort on bringing statistics and statistical and computational thinking together even closer. And I'm going to point you, and I'm sure he will do the same, to a recent report from the National Academy of Sciences on frontiers of massive data analysis, which is very relevant to the big data theme of this conference. He has received many awards, and I realized I never asked him which one are his favorite, but I'll just mention he's elected member of the National Academy of Sciences, the National Academy of Engineering, and he's recently won the Rumelhart Prize for Theoretical Foundation to Human Cognition. And despite all this impressive resume, I think his greatest achievement is the stream of amazing PhD students who, after working with him, go in the world and do great things, and many of them continue to be influential members of our profession. So let's welcome Michael.
Okay, thank you, Ado. So this is going to be a math talk. I've been giving talks on big data for about 10 years now, and I think fundamentally the phenomenon has become so important because of industry and kind of the empirical efforts in industry to build systems and change the world bottom up. But like in many eras, going back to Gauss, say, these applied problems lead to math problems. And I think that's really the topic of our day, of what new math problems are coming out of this area, how can we isolate them and build on them, and build a realistic approach to big data that really works. I'm going to make it short and sweet, my introduction to big data, but I can't resist using a little fictive kind of interview that of the talks I've given about big data over many years. This one seems to catch the most of the spirit. So I imagine one of my undergrads in particular who's just finished their degree and has gone down to, say, Facebook or Google or Amazon or whatever, and they're participating in an interview. So the boss says, I need a big data system, whatever that means, that'll replace our classic service, perhaps it's search, perhaps it's recommendation system, with a personalized service. Okay, so that's actually what's really different now. Instead of doing search for everybody or recommendations for everybody, you have enough data about every individual in some really huge population that you can aim to serve each individual in a reasonable way. Now there's these long tails, it's really hard to do this, but you really can aim to do this. And there are many business plans built on this. This notion of individual isn't just people, it goes over to genome region or region of the sky or region of the ecosystem. You know, we have enough data on every important kind of conceptual piece of many, many systems that we can aim to do analysis at that level. So that's what's new. Okay, so the boss continues, it should work reasonably well for anyone and everyone. So think L infinity norm. Okay, L2 norm is no good anymore. You've got millions and millions of individuals trying to serve, and if 5% of them are being badly served, they're going to write letters to the editor, they're going to complain, and your business is going to tank. All right, you've got to do something in the L infinity norm. Very, very different. All right, now it gets worse. All right, so far it's just sort of challenging, ambitious statistics. But now it becomes computer science, and at the same time. It should run just as fast as our classic service. So you're asking to be doing a huge amount more statistical modeling, controlling error rates, having hierarchical models, and so on and so forth. And it can't slow down because, again, our business model would tank at that point. Anybody whose search has been 2 milliseconds, suddenly it's 5 milliseconds, they're not going to be happy they get more services. They're going to turn you off. Okay? So how do we make guarantees on runtime and do statistical inference? Well, that we just don't know how to do. That is a problem for our era. Okay? We have heuristic ideas, but we don't have theoretical ideas. Now, it gets only worse, which is now I've got a large amount of data about all the individuals, but in 10 years, I'm going to have way, way more data. It's going to grow at some unknown rate. And I want to exploit all that data. I don't want to just stop collecting data now. And as the data grows in size and volume and blah, 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 the system should never get slower. Okay? How can it get slower? You're giving it more of a resource. You're giving it something good. Right? And so how can another resource get worse? How can the runtime get worse if you're providing more of a powerful entity called data, which allows you to make inferences? All right, so we have no idea how to manage that kind of trade-off right now. Keep runtime, maybe growing slowly, but under control as the amount of data grows. We need to know something about the risk of each data point and trade that off against runtime. Very hard to do. All right, and it only gets worse in the real life setting that I'm imagining here, which is the boss says, we also have big privacy concerns. Many companies have big privacy concerns. There's a lot of talk about one that's particularly interesting these last few days. And they vary across the clients. Some clients don't care about their privacy, others do. There should be a knob for each client to allow them to do this. And now you start to think of a real world engineering system. Hundreds of years ago, it was like build a bridge or build a building. And now it's build a system like this that serves a large number of people in the L-infinity norm fast and reliably and so on. That's what our goal is. So in some sense, all of us, I think, came up as mathematicians. This is engineering. This is kind of the information engineering of our age, and that's what I think the big data problem is all about. All right, so how are we going to do this? Well, we got to blend what I would call computational thinking and inferential thinking. I'm going to try to make that a little more kind of pungent as we go here. But computational thinking isn't just learning how to program in R or whatever. It's thinking about abstractions and modularity. It's modeling the world in kind of a computational way. And so that's what you learn if you take 4 years of a computer science curriculum. Inferential thinking is a whole different kind of animal. And you don't see it typically in a computer science curriculum. Just as you don't see computer science thinking in a stat curriculum. They're really, really disjoint, despite all the talk. So inferential thinking fundamentally goes to looking at the data and thinking about what's behind the data and processing the data so that you can say something about what's behind the data. Okay, so I'm going to give an example here that, again, I hope makes that clear. You will see lots and lots of work where people will run statistics on some kind of a data set, a database, or run a machine learning algorithm and purport to have kind of done inference. And that's not the case. So we'll be talking about that. Okay, now, again, this will be a theoretical talk. What are the theoretical issues here? And they're really daunting. There is a theory of complexity theory in computer science, going back to Turing and before, which gives bounds on and various approximations in runtime and space usage and energy and various quantities that are prescriptive to the problem. Very satisfying theory for some purposes, but not statistics, because there's no notion of risk in the theory. Right? And it's not, you can't just glue risk in, as we're going to be talking about. Similarly, if you look at the whole long literature, the statistical decision theory, where it focuses on risk and how it trades off with dimension and complexity and number of data points and so on, you will never see the word runtime. It's just not part of the statistical theory. All right? And these things don't just kind of glue together. This is a very, very big mathematical challenge. So here's the goal that's been driving me for the last few years, which is to be a mathematician. I really do think that the interesting questions here are theoretical ones, and find trade-offs, in some sense, rules of thumb. But that bring together statistical quantities with computational quantities. Okay? There should be a little bit of runtime, there should be a little bit of statistical dimension, there should be a little bit of complexity, and there should be notions like privacy, externalities, if you will, communication, privacy, and so on and so forth. Okay, so the talk is really a bunch of vignettes, a bunch of research papers where we've made some amount of progress on some of these problems, and I want to point to some of those ones where we haven't made progress, which they're just very, very hard, kind of to help motivate some of the audience to work on them. So privacy and communication are just kind of quick little vignettes to give you a flavor of how you can get a trade-off, what does it mean to get a trade-off, and can that be useful? And then I'll try to focus most of my time on computational constraints where it's really, really hard to kind of think of the fundamental quantities. Turing-like theory is not actually the way to go. What's going to replace Turing theory as we start to merge computation with inference. Okay, so John Ducci and Martin and I have worked on for this for about 5 years, inference, and trying to bring privacy, a quantity that's been talked about for many, many years in the statistical literature, but mostly very informally, bring it into statistics as a formal concept. And in fact, there has been a formal literature on it called differential privacy, rising out of the database and cryptography literature. So we want to blend that formal concept with formal statistical theory and sort of see what that blend looks like and what it buys us and what it gives us. All right, before I get formal, I don't think I say much on this slide, just basically the goal is going to be to give each individual who's giving some data to the data analyst a knob they can turn, which is how much they care about their privacy. And that knob has got to be responsive to the particular data and the particular loss function that's at play. If you want my genome and you're studying a disease that runs in my family and trying to make predictions for future individuals, then I'm happy to give you my genome. If you're trying to use it to sell me insurance or advertisements, then I don't want to give you my data. I want to turn the knob down. So we want the knobs to be tunable according to the loss. Okay, so let's first talk about kind of the computer science perspective on privacy. There has been a very, very impressive, very useful literature on privacy emerging. It basically has the following kind of character. There's a database. So think about bank accounts. There's people, their address, their height, their weight, or whatever, and then the amount of money they have in the bank. So it's a bank's ledger. All right, and you put a query into the database, which is, for example, what's the maximum account size, what's the minimum, what's the average, you know, whatever you care to ask about bank accounts. And out comes an answer, which I'm going to non-traditionally call theta tilde. Okay, it's some answer to some query. Okay, now, in the privatization world, you don't want to reveal who's in the database. You can't just let arbitrary queries come in and get out the answers. You'd reveal people's private information. So you apply some kind of a channel, you take the database and you push it through a channel, which is usually randomized, which fudges up the data in some way and turns it into a randomized database or a privatized database. All right? And now you're allowed to give some queries to the privatized database, and you can prove that under particular constraints on Q, you can't do things like test whether 8.0 was in the original database or not. You can't do a hypothesis test and have high power for the detections that you might care about. Okay, so differential privacy will apply to sets of randomized operators Q and giving guarantees about what you can know about the database based on looks at the privatized database. So you send your query into the privatized database and out will come an answer theta hat. And the whole theory of differential privacy is, or most all of the theory is, trying to say that theta tilde will be close to theta hat under conditions on Q that guarantee privacy and with high probability, because everything is probabilistic here. Okay? So this sounds like, and has been often treated by people in the database literature as statistics, because there are queries, there are answers, there's randomization, you're calculating statistics on the data, like the mean and the median and the quantile. What could be not statistics about this? It's a merger of statistics and CS. Well, I don't think so. It is in some limited sense, but not in the full sense. Okay? So now let's be statisticians. I'm going to shift the diagram over a little bit. Same picture as before. The query comes in the database, and out comes some kind of answer, theta twiddle. But as a statistician, you always think about where did the data come from? What's behind the data? In particular, let's think about not bank accounts and people's amounts in it. Let's think about medical data. I've captured a bunch of blood pressures and other measurements on people, and I saw their response to some drug or not. So the dependent variable, if you will, is not amount of money. It's did you die or how long did you live? Okay, so P is the population that can generate new data like the data that you got in your database. And S is a sampling operator. All right, so a statistician would then think, well, I can run that same query on the population. If it was a median, I can ask about the median of the population. So it's certainly a well-defined entity. And if I have that, if I know the median of the population, I can make really good predictions about future people, not just the people in the database. Okay, all right, so out comes an answer theta, and the statistical theory is fundamentally about saying that theta is close to theta twiddle under constraints on the sampling process, okay, IID or whatever, what have you. Okay, so that's an inferential picture, but now there's no privacy. All right, so the obvious next thing to do is to put them together. Now we're doing computational thinking and inferential thinking. We're gluing them two together, all right, which is you say, well, the people in the database, take the medical example. They may be dead and gone, right? But I still somehow care about their privacy because their offspring are still alive or whatever. I don't want to reveal who's in the database still, okay? But I'm not just trying to say things about the people in the database, like in the banking situation, because these people are dead and gone. I want to make predictions for new people, whether the drug works or not, and how long they're going to live, okay? So it's an inferential problem. It's not just statistics on a fixed database, okay? All right, so therefore, given S, sampling pattern that led to the database, I want to make predictions about P, and I want to do it respecting the privacy of people in the database, so I use Q under differential privacy. All right, and now the math question is to say, is theta close to theta hat, all right, with high probability across S and across Q, given the constraints that are natural to those two things? Okay, so I'm going to tell you about a little theory that does that, achieves it. It's one contribution in this area, but this is an emerging area. This is kind of the blend that we're after. Okay, if you can do this, I think you're doing something that society is really asking to be done. Okay, so we're going to be frequentists today. I recognize the previous two talks and maybe more were Bayesian. Certainly Bayesian paradigm is going to continue to play a role in big data. But I personally turn towards frequentist methods. Frequentist basically is not a kind of method, it's just an analysis style. So if you're trying to do mathematical analysis, frequentist is kind of natural because you have the analysis tools sitting at, and they allow any kind of method. So you just pick any method you like and try to prove something about it. So you have a lot more freedom in terms of kind of the statistical procedures that are available to you. And so I have found personally, and just going through many of these kind of vignettes, frequentist thinking is a good starting place for trying to develop new theory that's responsive to big data issues. Okay, so the frequentist theory we're going to use, I know there's a bunch of econometricians in the audience. You will know who Wald is, a blend of a statistician and econometrician. We're going to do statistical decision theory. So we have a family of distributions about which we want to make inference. There's a particular P in that family that we're really trying to ask queries about, just like as before. There's an estimator theta hat that tries to estimate some functional theta of P. And we have a loss function which measures how bad we are, how unhappy we are if theta hat is not close to theta. Then Wald said we need to then take an expectation over the data generating mechanism because theta hat is random under the data. So the expectation is for fixed P, it hits the theta hat, and now that result is a function of P. It's also a function of the particular procedure, theta hat, that you use. And we would like to compare, a couple of different, or a bunch of different kinds of procedures, theta hat. All right. Wald then also recognized it's a problem that's a function of P, because for one theta hat, I might get a certain curve as a function of P. For another theta hat, I get a different curve as a function of P, and they may cross, so there's no best curve. All right. So one way to get around that is to take a worst case perspective, take the supremum over the entire family P. Okay, so you take the worst case over the axis, the P axis, and you get a single number now for a given theta hat. And if my single number is better than Ato's for his theta hat, then I win. Okay? If you're a Bayesian, you can think of this as robust Bayes. This is the worst case prior. This is the Bayes risk for the worst case prior. Okay, so let's now try to blend that perspective. That was just my one page on the statistical decision theory, which still to this, it's 100 years old, but it still to this day, drives great amount of theory. So we're going to have private data, X. We're going to privatize it by a channel Q, just like before. And then we're going to apply the estimator, theta hat, to the privatized data Z. All right? And we're going to start making some statistical assumptions. We will assume IID draws of X from the distribution P, but the estimator can only look at Z. Okay? Here's the one-page definition of differential privacy. I don't want to spend much time on it, but just to say it's nothing to do with P and nothing about the query. It's about Q. So it's a ratio of Q evaluated on one data set X and comparing that to Q evaluated on a different data set X prime. So X might be the database with me in the data. X prime is that I've been extracted from the data. I want to say, can I distinguish between those two databases? All right? And if that ratio over the whole sigma algebra, everything that an adversary could choose to look at, S, is small, where alpha tunes the amount of the size. If that's small over all X prime and events S, then I have differential privacy at level alpha. Okay, so it's kind of a band on it's a likelihood ratio, and it's a band on the values that the likelihood ratio can take on. Okay, so there's a literature, this goes back to 2006. It's a powerful literature. It does things like, it has a compositionality property. If I protect differential privacy at level alpha 1 on one database and at alpha 2 on a different database, if you join the two databases into some arbitrary way, which often can reveal a lot, you may have read about that, you protect differential privacy at level alpha 1 plus alpha 2. Okay, so you can query, you have a budget, and it gives you that notion of a budget. So I really like this formulation, and we're trying now to bring that into contact with statistics. All right, so our approach is going to be very, very straightforward. It's going to be constrained optimization. So there's a bunch of symbols here. They're not that complicated, though. So the expectation over P of the loss function, that was just Wald. And moreover, Wald added the supremum over P there to get the maximum risk. Okay? And then Wald also said, let's take the minimax risk by taking the infimum over procedures, get the best procedure under the maximum risk. So everything from the blue on is just Wald. All we're doing is adding the first infimum over all channels which respect differential privacy to level alpha. Okay? And the theta hat can only look at z, which is an output of q. So now we take an expectation over p and over q. So it's that whole picture that I told you about before, just put into a single, somewhat traditional optimization formulation. All right, now is that interesting? You can write that down. Is it interesting mathematically? And the game is going to be to do like what people in statistics do. In statistics, you can solve that minimax risk. At the infimum of the supremum, you can get a often asymptotic formula which says how does that vary with n? It goes as 1 over square root of n or 1 over n or something. How does it vary with the dimensionality of the problem? How does it vary with a bunch of other statistical parameters you care about? So you can do math on that formula. And the question is now can you do math on this expanded formula, okay, that includes alpha. So it's good. Now if you do that math, you get out a functional that goes down as n, and it goes down with or up with d, the dimension of the problem, but also alpha will appear in the formula somewhere. And it'll be interesting to see how it trades off with the other quantities. Okay, so let's just look at a little example I think is the best way to understand what we've been able to do here. So let's suppose people have been admitted to hospital and they abuse various substances. This particular person abused alcohol and cocaine and nothing else. And people are coming in with that as the truth. You would like then the data, and then the underlying proportions in the population, suppose we're given by these numbers. 45% of the people abuse alcohol and so on. If we could infer those things, we would know how many hospitals to build, how many doctors to have in the hospitals, and so on and so forth. So we'd like to infer that. If we had that data, we'd just do maximum likelihood under the multinomial distribution and get sample proportions, which would approximate those things as uniformly blah, blah, blah. All right, but people don't want to reveal that kind of data. Okay? So we're going to put it through a channel and see, what can we still control? We can control their privacy at level alpha and see what kind of statistical risk do we get. Here's the classical minimax risk. It goes as 1 over square root of n for this particular problem. And it goes as logarithm, square root of logarithm of the dimensionality. D is the number of components of the theta vector. Okay, super classical result. Nothing exciting there. Okay, that is gotten by solving that infimum of supremum of the particular, this is L infinity loss on a non-parametric set, all distributions supported on a compact set. Okay, so that's a little piece of math you can do after 1 semester of math stat. All right, now if we solve the new problem, which included the infimum over alpha, or over Q alpha, here's what happens. I should say a little bit more math is needed, some geometry fundamentally. This is kind of some convex geometry. And you get the following result. N is replaced by n alpha squared. So alpha does appear in the formula, and it's a pretty nice place to have it appear. Because if alpha is like nearly 1, and you want to get the same risk as before, okay, suppose that alpha is 0.9. You just got to up n a little bit so that n times alpha squared is the same as n was before. All right, if alpha is a half, that people care more about their privacy, alpha squared is a quarter, you got to collect 4 times as much data, you'll get the same risk as before. And you know this a priori. This is a math result. So this is something I would want to give to as guidance to someone collecting data. Here's the people are asking for that level of privacy, just collect more data. And here's how much. All right, problematically, log d in the numerator goes to d log d, okay? So this suggests, and it's true, that in high dimensions, differential privacy is really hard to achieve. You're trying to protect in all directions, there's a lot of directions, and so I think that one interpretation of this result is differential privacy is probably too strong for high dimensional statistical problems. We're going to have to develop something else, and that's an open problem. Okay, so the effective sample size went from n to n alpha squared over d. How am I doing time? Okay. Okay, so it turns out that for a whole variety of other statistical problems, that exact same formula holds. So I would propose this as a little rule of how differential privacy meets statistics. Okay, so I'll show you the list on the next page, but there's some generic geometry kinds of reasons why this formula is arising, sort of geometry and information theory reasons, and I think it can be viewed as a general law. I'm going to skip a little section which I don't have time for, which is these are all theoretical bounds. The question is, as usual, are there any procedures which achieve these theoretical bounds? Okay, and that turns out to be yet more interesting. The usual procedure in the differential privacy literature is you add Laplace noise to your data, heavy-tailed noise. If you add Gaussian noise, you can see easily you don't protect differential privacy. It's too weak. If you add heavy-tailed noise, you can protect privacy at level alpha. But it turns out, statistically, that if you add Laplace noise, you get very bad, poor risk. Okay? It's not good from the point of view of risk. It hurts you too much. All right? So you ask, well, it doesn't meet the lower bound. It doesn't meet this bound. And it's quite much worse. Is there some other mechanism which is better than adding Laplace noise? And it turns out there is, and the theory guides you to that, and in a longer talk I would go through that. We have a paper which lays out the optimal mechanism and then gives some empirical results comparing to Laplace noise addition. So I'm going to skip those slides that go through that. There's the empirical difference. We have a paper which goes through a whole bunch of other statistical problems, adding in the infimum over Q alpha and showing that this generic result arises. All right, so that's my little vignette on kind of an example, kind of almost a thought experiment of can we add a quantity, Q alpha, which has not been in the statistical framework, and what happens when you do, and kind of some of the results that are coming out. Let's do something similar with another kind of, maybe computationally oriented quantity, which is communication. So a very similar setup, pictorially, but different conceptually. We're going to imagine our data are so huge, terabytes or whatever, so that I cannot bring them to a central machine. All right, it's going to take me too long to do it. I have to ship disks around or something. So we want to say to the statistician, you can analyze your data, but you can never bring the data together in one place. Okay, so not just parallelism, but real distributed computing. Okay, you can't have shared memory. Okay, so therefore, what am I going to do? Well, I'm going to compress the data locally from X down to Z, and then I'm going to send the compressed data to the central site. All right, now what do you mean to compress? Well, didn't Shannon tell us how to optimally compress? Well, yes and no. Shannon told us how to compress to make bit length small, but not how to optimize for statistical risk. You can make bit rate small, but your risk could be terrible. You have to control for risk as you're doing the compression. So can we get a theory that replaces Shannon that says that you're trying to optimize for statistical risk, and what's the best compression protocol that achieves a certain level of statistical risk? By the way, this is work with Yu-Chen Shang and Martin, as well as John on this paper. Okay, so I'm just going to kind of cut quickly to the chase here. We're constraining the channels to have capital B bits. So B is like alpha before it's the new parameter, which we need to get into a trade-off. And here's the math problem we have to solve. We're using L2 loss in this particular example. This is going to be a location parameter of a Gaussian distribution, the mean, and we're going to estimate that in the L2 norm. Okay, so the question is, how can you solve that optimization problem for all channels which compress to level B bits? That's the bit rate. So here's going to be our example. We're going to do a d-dimensional Gaussian. We want to infer the location parameter. The classical minimax rate is right here. It's the dimension of the problem d in the numerator, divided by the total amount of data. There's going to be m machines, and there's n data points per machine, so nm is the total amount of data. So this is a parametric rate for this particular, it's a parametric problem, the classical minimax rate. So now what happens when you add the extra infimum over channels that have a bit rate b? Now the new rate is the same minimax rate as before, 1 over nm. And now there's a new factor out front, which goes as logarithm of the number of machines, log m. So it's very favorable. I can have lots and lots of machines, and I still have good control over my risk. And now, interestingly, B and D occur together. So B is the bit rate, the communication part of the problem. D is the statistical dimension of the problem. What if I choose, I get to choose B. I pay money to get the bit rate to some value, okay? And you told me the dimension D of the problem. So once I saw D, what if I choose B to be equal to D? All right, then the minimum of B and D just become D, and D cancels in the numerator denominator. I get a dimension-free result at that point. Okay, so that's already kind of interesting that you can do that, but what's, I think, really interesting is that it couples these two quantities, the communication Shannon part of the problem and the statistical complexity part of the problem, the dimensionality of the parameter vector. And there was no a priori reason to think that those would be coupled. But the theory tells you that they are. Okay, so I'm going to leave that thread behind as well. I just wanted to, that's the main remark I wanted to make about that. And the remaining part of my talk, say a few words about some other vignettes about we're starting to get to the hard part of the problem. Okay, so that agenda of taking minimax risk as a good example of a statistical solid theory that has 100 years of development behind it, and trying to expand it out to include other externalities that are societal related or economics related or whatever, I think is a very valuable agenda. Okay, so we've had some examples, and there's others as well. Computation is such a hard thing to think about. Turing kind of helped us, and others have been, there's a whole complexity theory that helps us, but I don't think we're there yet. I don't think we kind of have the solid kind of concepts that allow us to glue into statistical inference. I think this is still hard. And so I'm going to tell you about some vignettes that do not solve the problem, but kind of aim at aspects of it and again, try to motivate some further work. So worked on it a bunch recently. We had examples of papers that my group and I have been working on. I'm going to sort of, in the spirit of vignette, just give you a little flavor of how a couple of these go. This is kind of long talk shrunk into 5 minutes. One way is to try to use geometry and relate runtime to geometry. That's kind of a thing that's been done in the computer science literature a lot, in the optimization literature, and relate geometry to statistics. That's a thing that's been done in the statistics literature a lot. And that relates runtime to statistics for this bridge. So that was one of our first papers on this trade-off. And I think I will briefly mention how that goes. Another one is to borrow ideas about parallelism from the computer science community, and particularly the database community, where it's not just about parallelizing, it's about parallelizing and still retaining some notion of correctness. So concurrency control is very broadly used. I mean, bank machines use it and so on and so forth. We want to get ideas out of that to inspire us in statistics computation trade-offs. Another way to go is to kind of get rid of computer science altogether and go to optimization theory as your kind of way of supplying a notion of computation. The number of times you get to see a gradient, that's a surrogate for computation. Okay? Think of that as unit amount of computation. I show you the gradient m times. You've paid cost of m. And there's a lot of work. The Russians, Nesterov et al., kind of giving us notions of oracles for lower bounds and matching procedures for that notion of computation. So I think I have some work on that, but I'm not going to talk about it. Communication complexity is another kind of CSE kind of way to go about it. And then I guess the last couple of talks illustrate some of the elephant in the room sort of is that we can get large numbers of new machines. All right, we can only make modest improvements with sampling or with algorithmic improvements, but we can throw more machines at it. We want to do theory there. How much better can we do as the number of machines grows in terms of statistical risk, dimension of the problem, and so on and so forth. And to me, that is really, really exciting and very open. I worked a little bit on this, but mostly not very theoretically. These are mostly just procedures that have nice properties and mostly investigated empirically, which I think is probably where we are right now, but I think this is right for emerging theory. Okay, so just very briefly, let me mention a line of work that I did that's kind of early, but still I think this kind of a mathy conference helps make this point about geometry. Work with Venkat Chandrasekaran, who's at Caltech. Okay, so we're trying to, in this case, get trade-offs, right? Just like in the rest of this talk. In particular, minimally, I want to put together a statistical quantity, which is number of samples, with a CS quantity, which is runtime. And there has to be a third axis, which is the risk. We always have to have the risk in the picture, otherwise we lose the whole point. All right, so there's a surface, and we would like to get upper and lower bounds on that surface and as tight as possible, and then get procedures that allow us to move along that surface. That's what, in 50 years, if we had that, we kind of could feel satisfied. So one way to get at this surface, there's been various people working on this. The way we made progress was to take a slice on the risk axis, so fix the risk to be 0.05, or if it's a 0.1 loss, or some other value, and then get a curve that relates runtime and number of samples. So it'll typically be a trade-off curve like this. It'll go down. It'll flatten out at some point, which is the point where you should be throwing away data. You can do no more. And we want to get a characterization of that kind of curve. All right, so here's the little kind of, I think of this as the Bohr atom of statistics. It's called the denoising problem, used to great effect by Donahoe and Johnston. That allowed us to finally make a little bit of headway on this theoretically. So it's just y is equal to x star plus sigma z. So it's like regression where the A matrix is the identity. It's the simplest possible problem in statistics. All right, so we have z is going to be Gaussian noise here, p-dimensional Gaussian noise, and x star is the unknown signal, and it lives in some set S, and that's the only complicated part of this slide. The signal set S is going to be possibly discrete or combinatorial, and to find a signal in that set may be computationally challenging. Okay? So again, I'm going to kind of go quickly here. The details are not so important. It's going to be the kind of what's the overall story that I want you to kind of get a flavor of. So we had IAD samples, so let's take a sufficient statistic as our actual data. Y bar is now viewed as the data. And let's turn this into an optimization problem. It's called M estimation in statistics. So compare Y bar to an estimator X in some norm. This is the L2 norm, and minimize over all X in the signal set S. That would be the most natural starting place for optimization formulation of this problem, and call that your estimator X hat. Okay? Now, that's probably going to be intractable. If S is discrete, it'll be an integer program. If it has some structure, it still might be intractable. And moreover, we would probably overfit if we tried to allow ourselves to explore all the vagaries of the signal set. So for statistical and computational reasons, you probably want to relax the problem to a outer bounding convex set, C, and optimize over that, and get an estimator, which we could call now x hat of C. Okay? Now, the game in this little line of work was to then look at nested relaxations, C1, C2, C3, C4, all right? And think about that both computationally and statistically and see if we get a trade-off curve, okay? Computationally, as you relax further and further and further, there are many such hierarchies known where the computational load gets less and less and less and less. You start with you start intractable, then a semi-definite program, second order cone problem, linear program, and so on and so forth, okay? And there are rates known for these kind of things. Statistically, surely, as you relax more and more and more, you're going to maybe do better for a little while while you get rid of the overfitting, and then you'll start to do worse and worse and worse, okay, as you allow too many estimators into your problem. So if we can calculate that second trade-off, we can put the two together, where the geometry is the intermediate. You know, the geometry is this set of nested relaxations. That's playing the intermediate role here. Okay, so there's just a little picture of the example of a signal set S and the convex relaxation C. This truth might be a corner point here. Well, actually, it's in the signal set S, so it's got to be a corner point of the convex hull C. And then there's a little theorem which allows you to kind of pull these two things together and get a trade-off. And so this theorem has the risk on the left-hand side. There's a lot of equation here, but it's really quite simple. On the left-hand side is just the expectation of the loss. That's the risk. That's walled. Okay? On the right is 1 over the sample size, pretty good. And then there's a big old long quantity there, which is a object very close to something known as a Gaussian width. It has nothing to do with statistics. It's just a piece of geometry and probability. And what it's doing is it's taking the inner product between a direction delta in the tangent cone to x star. So the tangent cone, I think I went over that quickly, just all the directions locally within the set C's, leading from x star. And as the set starts to grow, the tangent cone grows in size. All those directions grow. And we're taking inner product between a particular delta and Gaussian noise z, and then taking the expectation over z. Okay? So it's a width notion that brings into a particular probability distribution into this notion of width. So as c grows, that expectation on the right-hand side will grow in size. And now the question, again, is a mathy kind of question. Can you calculate that as a number, as a function of n, for various interesting geometries? If you can do that, we got some math going. Okay, so if you turn that equation around, and now, as I said earlier, we're going to fix the risk on the left-hand side to a fixed number, say 0.05. And now you can rearrange that equation. You can say to guarantee a risk of at most, without loss of generality, 1, doesn't have to be 0.05. Then all you got to do is choose n to be greater than or equal to sigma squared, the noise level, times that Gaussian squared complexity, which is just a number. That's a function of just the geometry C. Okay? So there is a trade-off, right? If I know the geometry, I can calculate that number. I can get a relationship between risk and amount of data, and bring in computation, because computation will depend on C. Okay, so now we start looking at hierarchies of these things. C is nested within a C prime. And to go further, there are a whole bunch of hierarchies existing in the combinatorics literature that represent sequences of relaxations, and they are ordered by computational complexity. Okay? All right, so I'm going to skip ahead. We have a bunch of examples here. I wanted to show one particular example. Yeah, here's my favorite example. Okay, so this is the setting where we're trying to do high-dimensional covariance estimation. So suppose that the dimension p is larger than n. All right, so covariance matrix is p by p, and so p squared is definitely larger than n. We can't estimate all the parameters of that matrix with n data points. So people would look at banding estimators, which most of the entries are set to 0, and only a few of them are actually estimated from the data. Well, that assumes you know how to order the variables. So there's a note there, you get a banded matrix. Okay? What if you don't know how to order the variables a priori, like in a biological example of networks? What's the order of the genes? And I don't know. So the inferential problem, kind of combinatorial inference problem, is to find the ordering. So let's call that pi. It's a permutation matrix. And so the signal set is the orbit of that permutation, just all the matrices you get from taking a banded matrix and running over those permutations. Okay, so I want to optimize over that signal set, and even optimizing the L2 norm, that's intractable. So we start to relax to the convex hull, and then we relax further to the scaled L1 norm ball. The first column is just borrowed from the CS literature. It's the runtime associated with those geometries. There is an algorithm which will optimize over the convex hull of that set, which is known to be super polynomial in the dimension P. And then if you go further relaxation, you get a cheaper algorithm. So as usual, you get cheaper and cheaper algorithms as you go down. And here's the new column, which is gotten from the formula I gave you a few slides ago. This is the statistical complexity of the problem. And it has to go up. You have to get worse as you go down. But it turns out it goes up only in the constant. And we can compute these constants. So there you go. It's actually constant in the dimensionality of the problem. So this suggests that as you go down to these relaxations, the statistical risk only slowly increases, whereas the computational complexity drops a lot. Okay? So it gives you a trade-off that favors cheap algorithms, cheap, fast algorithms. All right, so that's kind of been a folk theorem that for big data, cheap, fast algorithms are the way to go. And this is a real theorem that shows that in a very stylized situation. All right. Okay, last couple of minutes are going to be less mathy, but I'm making a mathy kind of point, but I'm going to do some cartoons. Okay, so as I mentioned, I called this the elephant in the room earlier. The one knob we can really, more or less easily turn these days is, having thousands or tens of thousands of computers. So how does that impact statistical inference? That's the agenda item for many, many of us. All right. I'm going to do this with some pictures here. Late in the talk, I decided to throw out the math and just swap in some pictures. Let's think about the kind of the broad class of problems where we have a parameter vector of some kind. That's going to be the model parameter vector. And each data point has a gradient with respect to those parameters, and that gradient's sparse. All right, so for example, the second data point there, its gradient only depends on theta 1, theta 4, and theta 6. And each data point refers to a particular subset of the parameters. Okay, so that's characteristic of many, many algorithms that are widely used in practical machine learning applications. And now let's take kind of a CS point of view on that. How can we update the model in parallel? If we have split up the data over multiple machines, like you saw in the previous two talks, we're not in a Bayesian paradigm right now, we're in an optimization paradigm. How can you update the model and not engender too much conflict that may be damaging to your overall statistical risk? Okay. So there's a variable that's getting read. We're going to, in general, have each data point touching a subset of the variables, and there may be some overlap. Or conflict. So, three kind of meta-theoretical perspectives have been emerging. Well, two have really been emerging. The third one I'm going to just briefly mention with something we're just working on right now. Hog wild really refers to a shared memory paradigm where you don't have to communicate the parameter vector a lot. You allow the different processors to just write over each other in a shared memory paradigm. And under sparsity assumptions and not too much delay kind of assumptions, you can show this is not going to hurt you very much. So that is a very useful perspective. When it came out, people were surprised that this could be as successful as it is, but it has been successful, and there's some nice theory associated with it. So it's kind of the benchmark right now is to beat hog wild, and some problems it's hard to do. Optimistic concurrency control, this is a little bit heavier machinery that comes from the database literature. So if you and me are updating, or my wife and I are updating our bank account, and she's in Berkeley and I'm here, and we do it in the same microsecond, we want if I take out $5 and she takes out $5, we want to get $10 out of the bank account. At least the bank wants that. And you want to do that over the 3 billion people who are currently using the banking system. So they've worked that out. So the machinery they have does that. No conflicts emerge. They can prove it, and it really works. So we want to borrow some of their ideas in this statistics setting and see if we can make guarantees that, again, tie in the risk. So I'm just going to briefly mention some work we've been doing. I have several papers now on that. And then lastly, graph theoretic perspective. We've been kind of just starting work on that, and I wanted to just kind of highlight it very briefly. Okay, so optimistic concurrency control is optimistic. It refers to the notion that you're going to pretend that conflicts do not arise. And if they do arise, you could detect them and roll back a little bit and patch them. Okay? So that's going to be a really good model in situations where mostly conflicts will never arise. You can go forward in parallel. If they do arise, though, you need to be able to detect them. So I'm going to give you a statistical example of why that might, where that might be naturally applied. Okay, and I'm about to finish up, right? You know, I got like a minute or two. Yeah. So this is a little algorithm that Brian Kulis and I proposed about 3 years ago. It was based on the Dirichlet process, but it's really best thought of as a version of k-means. So the k-means algorithm is a clustering procedure where you assume you know a priori the number of clusters, and you assign each data point to a cluster, and then you move the clusters according to the centroid of its assigned data points. What if you don't know the number of clusters, k a priori? Well, you're inspired by the idea of the Dirichlet process to turn that into an optimization procedure on its posterior mode that leads to a k-means-like algorithm where you don't know k a priori. And just let me show you the picture. It's a sequential algorithm. I go to the first data point and I say, is there a cluster centroid near you? There is not, so you become a cluster centroid, where near is some parameter lambda of the hyperparameter of the algorithm. Then I go to another data point, and is there a center near you? Yes, so I don't create a new cluster centroid at that point. All right? And then I go over here, and I create a new cluster centroid, and then here, and similarly. So it's a very sequential paradigm, no parallelization going on here. Right? What if you then, and then you update the cluster centroid just like in k-means. Now, if a data point is, of course, beyond lambda from any current data point, you will create a new cluster centroid. All right, what if you try to do this in parallel? Well, if you're far apart, then you can do that willy-nilly, and there's no problem. You'll have no conflict. But at some point, you may choose two data points which are close. It may not happen very often in high-dimensional space, but it may happen. When that happens, you need to be able to detect that it occurs, and there's a simple hashing procedure that allows you to do that. And then, oops, roll back and sequentially execute that little step of the algorithm. So you will now guarantee that you're the same as the sequential DP algorithm, but hopefully getting speed ups. So optimistic assumption, validation, and resolution. Okay, so that gives you hopefully a little flavor. There are many other we worked on submodular problems and others where you get a flavor, there's kind of this combinatorial structure which you're trying to keep coherent across parallel updates. And I want to just show you, I think, one example of it. Here we go. So this is this is a real large-scale problem, real big data. 140 million data points, 1, 2, 4, and 8 machines. And this is for that DP means problem. And this is just a runtime plot. So the theoretical linear scaling you would get is a dashed curve under there, and the actual scaling was a blue one. Okay, so in this particular example, on a real-world problem at really, really large scale, this was gets full advantage of parallelism. Okay, I want to skip over. There's another project. Let me just mention some names of people called Cyclades that we're currently working on. A paper will appear soon, where you do some more heavy graph theoretic machinery, but use randomized graph protocols to kind of break a problem into pieces with high probability under a random graph perspective. And I'm going to just skip over that because I don't have time. Okay, there I'm done. That was a bunch of vignettes. Apologize for the lack of detail in some of these. The meta message, I hope, is clear, is that this field of big data, I think, is two things. It's build big systems and build industries on top of them and see where you can make society change. And that's what industry is doing. You will see huge numbers of conferences on big data, especially on the West Coast, with thousands of people attending them. And they're all building systems. Okay? That's great, but I think there's a counterpart to that, which is the mathematical side of the field, which is to figure out what are the new conceptual problems here. And because we need to solve them, not just to pretty up what they're doing, but also to avoid all the huge numbers of type 1 errors and type 2 errors and statistical problems that they're going to run into when they just start building these systems and hope that they work. And that's a whole other talk of its own, is kind of the peril of big data, not just the challenge and the beauty of it, but the peril of it, which is building uncontrolled inference systems for huge numbers of people in society. It's just we can't do that. So we have to, as mathematicians, put on our hard-nosed analysis hats and start to figure out what are the problems here. Okay, I'm done. Thank you very much. Back in the back. Yeah, this is the local model. So if you're a DP guru, you know that's not the general model that's analyzed. We've analyzed only the local model. You will get one in the non-local. We just haven't done that work yet. Yeah, thank you.
All right, thank you, Michael.